Let's take a look at example 3. The hull of a cruise ship contains a vertical circular viewing window with a radius of 3 feet. And we're told that the top of the window is 12 feet below the surface of the water. We want to know, what is the fluid force exerted on this window? How many pounds of force does the water exert? And we are told that the weight density of water is about 62.25 pounds per cubic feet. So let's go ahead and try this problem. First of all, let's draw a picture to try to understand what's going on. We have a circular window here, and it's going to be useful to introduce a coordinate system. So let's say that this is centered at the origin, and we're told that the radius is 3 meters. So we can actually write an equation for the formula for this circle. X squared plus y squared equals the radius squared equals 9. So that's an equation that describes the window, and we are told that the top of the window is 12 feet below the surface of the water. So here's the surface of the water. This distance is 12 feet. And since the radius of this circle is 3, we know that the distance from the x-axis to the surface of the water is 15. Now, we want to know how much fluid force is being applied to the entire window here. And the issue is, near the bottom of the window, there's a greater amount of force than there is near the top. So as we go deeper, the force increases on this window, and we want to know how much total force is being applied to the whole thing. So as we've done before, we will take a slice of this window, and we will try to understand how much force is applied to a single slice. So we'll slice this up horizontally. Here's a representative slice. And we want to know how much force is being applied to this representative slice. So we want an expression for the force on a representative slice. Now, since this slice is parallel with the surface of the water, we can estimate the depth as being constant here. We have a constant depth, so the force is simply equal to, well, it's some small amount of force, dF. So this is equal to the pressure times the area of this thin two-dimensional slice. The formula for pressure is mass density times gravity times depth, and then we have the area still. Now for this problem, instead of having a mass density rho, we are given a weight density. We're told that the weight density of water is 62.25 pounds per cubic feet. Weight density is mass density times gravity. So this rho times g, that altogether is 62.25. We don't need to multiply by acceleration due to gravity because we already have a force per volume. So rho times g, that's 62.25. Distance d, that's the depth here. So how do we get an expression for the depth? Well, let's imagine taking this slice, since it's horizontal, and since we're moving the slice up and down, this is some height y above the x-axis. So this is at a height of y. That means that the depth from the surface of the water to where this slice is, well, in total, this distance to the x-axis is 15. We have a distance of y here. So the depth will be 15 minus y. That's what we use for depth. So the depth, 15 minus y. Then we multiply by the area of this slice. Now this slice is a rectangle. It has some length, and the width of the rectangle is the small change in y. That's this dy. Let's just call this length L for now. So the area is the length L times the width. So we have 62.25 times 15 minus y times L dy. How do we get an expression for this length L? We need to get this in terms of y, because ultimately we want to integrate with respect to y. So how do we get an expression for L in terms of y? Well, L is a distance along the x-axis. And if we think of this distance as x, the distance from the y-axis to some point on this circle, if this is a distance x, then L is twice that because we go to the positive and negative side of the y-axis. So we could think of L here as being 2 times x. And we can get x in terms of y by solving this equation of the circle for x. So let's do that. We get x squared equals 9 minus y squared. Take the square root of both sides, and we have x equals plus or minus the square root of 9 minus y squared. Plus the square root is the positive x direction, minus the square root is the negative. Now we're just doing 2 times the positive x direction. So L, if it's 2 times x, we're just going to use the positive square root. So L is 2 times the positive square root of 9 minus y squared. This expression is the width of this horizontal slice. That's that width L. So once we have that, we can write L in terms of y, and then the entire expression here has only the single variable y. So this is 62.25 times 15 minus y times L, which is 2 times the square root of 9 minus y squared, dy. This expression tells us the force exerted on just one thin slice of the window. In order to find the total amount of force, we'll simply integrate this expression with respect to y. Before we do that, let's double check that the units are working out as we want them to. 62.25 is pounds per cubic feet. 15 minus y is a distance, so that's measured in feet. The 9 minus y squared with the square root, that is also a distance, so that's measured in feet. dy is a distance, that's the small width of the slice, so that's also measured in feet. And then we can imagine canceling feet cubed, and we have units of pounds left over. That's the correct units of force for this example. So the final answer here, the total amount of force, is the integral. We integrate 62.25 times 15 minus y times 2 times the square root of 9 minus y squared dy. We are integrating with respect to y, and in order to get all of the slices of this window, we need to integrate from a y value of negative 3 to a y value of positive 3. This circle has a radius of 3, so we go all the way from y equals negative 3 to a height of y equals positive 3. Those are the limits of integration. This integral describes the total amount of force applied by the water on the entire window. Now, I'll just mention here that we don't actually have the resources to solve this integral by hand. This requires something called trigonometric substitution, which is not a topic that we've covered, so we'll rely on Mathematica to find the value of this integral. If we plug this into Mathematica, we get 26,401.2 pounds. This is roughly equal to the weight of 2 African elephants, and that's how much force is being applied to this submerged window. Let's solve example 4. Here we have a triangular tank that is filled with oil, and we're told that it is 1 meter tall, 3 meters long, 2 meters wide at the top. We want to know, first of all, what is the pressure at the bottom of the tank? We will compute the hydrostatic force on one triangular end, and then we'll compute the hydrostatic force exerted on one of the rectangular sides. So we'll start by drawing a picture. So here's our triangular shaped tank. We're told that it has a height of 1 meter, and it's 2 meters wide at the top, and the length here is 3 meters. So this is full of oil. Let's write down the density. The density of the oil is 800 kilograms per meters cubed. First of all, for part A, we want to know what is the pressure at the bottom of the tank. The formula for pressure is density times gravity times the depth. So here we have a density of 800 kilograms per cubic meter, 9.81 for gravity, and the depth here is 1 meter deep. So we multiply by 1, and the number here is 7,848 with units of pascals, which is newtons per meter squared. So that is what the pressure is that the oil exerts on the bottom of the tank. This is not the accumulated force, but it's what the pressure measures along the bottom of the tank. Now we want to know, what is the hydrostatic force on one of the triangular sides? So in order to solve this, we're going to imagine slicing up one of the triangular cross sections horizontally. So we'll take a slice here of the horizontal cross section. Let's say that this is at a depth of x from the surface. So this has a thickness of dx. And the width here, let's just call s. So for part B, we want the total fluid force on one side, and we start by finding the force on a representative slice. So this is some small amount of force, dF. Force is pressure times area. Pressure here is density times gravity times the depth, which is x. And the area is the area of this rectangle. So we have side length s times dx. So area s times dx. Now we have a problem here. We have s, but we want everything to be in terms of the variable x. So we will use similar triangles to write s in terms of x. So let's start by drawing a cross section of this trough. This is a height of 1, this is a width of 2, and we have this small slice of the triangular face. This is a length s. This length is x from the surface, and so the height of this small triangle is the total height 1 minus x. So this height here is 1 minus x. Now we have the width of the small triangle divided by its height. That equals the width of the whole thing divided by the height. So we can write s in terms of x. So we have s divided by 1 minus x. That equals the corresponding length 2 divided by the corresponding height 1. So this tells us that s equals 2 times 1 minus x. Now we have an expression for s, all in terms of the variable x. At this point, we're ready to write an integral to find the accumulated force on the entire triangular face. So the total force here is the integral of rho, and instead of rho, let's write 800, that's the density, times gravity, 9.81, times x, times s, which is 2 times 1 minus x, integrating with respect to x. The limits of integration are for the variable x, and since this is full of oil, x changes from 0 to the entire depth of 1. So we integrate from 0 to 1. This integral describes the total amount of force applied by the oil to one of the triangular ends of this trough. If we evaluate this integral, we get an answer of 2,616 newtons. Now you should double check, take a minute or two, and make sure that the units here work out to be units of newtons. And we can follow through and make sure that we're doing everything correctly by tracing through the units. So we get a final answer here. The force on one side is 2,616. Now for part C of the problem, we want to know how much hydrostatic force is acted on one of the rectangular sides. This is going to be a little bit different because the sides are not perpendicular, they are a little bit slanted. So when we find the hydrostatic force along one of the sides, it's going to look a little bit different from a vertical end of the trough like we did for this triangular section. So let's work through the details here. For part C, let's go ahead and just draw in what one of these rectangular sides looks like. Looks something like this. And here we have a height of 1. And this is half the trough here. So if we imagine half of the cross section of one of the triangular ends, well, the whole length here was 2. And if we just take half of this, then this length here is 1. So we have 1 by 1, and then here's our rectangular shaped side of the trough. So we want to know the total fluid force applied to one of these slanted sides. Let's go ahead and draw in a representative slice and think about the force on a representative slice. So here's a representative slice of the side. And there's a couple different ways that we could do this. We could measure the distance of this slice vertically, and we could solve the problem that way. But I think it's a little bit easier to measure the distance of the slice along the horizontal. So let's call this distance L along the horizontal, and we're going to want the total length of the horizontal here. So focus on this triangle right here. The horizontal is the length of this hypotenuse. That's, we could call the slant height. And if we have legs of length 1, then using the Pythagorean theorem, the length of the horizontal will be the square root of 1 squared plus 1 squared. So the total length of this horizontal is the square root of 2. If we think of the picture that we originally drew here, what we're saying is that this length, the slant height, is the square root of 2. So if we take a representative slice somewhere along the side at a length L, a slant length, then this will have a width of dl. Now let's try to find an expression for the force on this slice. Once again, we use the expression force equals pressure times area. The pressure is density times gravity times the depth. Now we need to be careful here. The depth is not L. L is measured along the slant. So the depth here needs to be completely vertical. Let's draw another picture of the cross-section to try to understand what's going on here. So this length is the square root of 2, and the height here, the total height of the trough is 1. And we're imagining this distance L to our representative slice. So if we think here, this is where the representative slice is. We want to know how deep that slice is. That's the distance right here. Let's just call this distance D. Now notice that we have a small triangle here that is the same shape as this triangle here. We have two similar triangles, a small one here and the larger one here. Since we have similar triangles, we can relate the side lengths using the ratio of corresponding sides. So I can write the height of the small triangle divided by its slant length L. That equals the total height of the overall triangle divided by its slant height, which is square root of 2. So this tells me that the depth D is L divided by the square root of 2. This is the expression that we must use when we use the formula for pressure. This slice is at a depth of L divided by the square root of 2. So going back to our formula here for pressure, we have density times gravity times the depth, which is L divided by the square root of 2. The area of this slice is the total length of the trough, which is simply 3. So we have a length of 3 times the width, which is dl. So we have 3 times dl for the area of this slice. This was fairly involved, but once we have an expression for the amount of force on one slice, we can simply integrate to find the total amount of force on one side of this trough. So the total force here is the integral of rho is 800, times 9.81, times L divided by the square root of 2, times 3, integrating with respect to L. And now we want the limits of integration. L, once again, is measured along the diagonal here, along this slant length. So L begins at a height of 0 and goes the entire length, which is the square root of 2. So the limits of integration are from 0 to the square root of 2. So this integral describes the total amount of force on one of these rectangular shaped sides of this trough, even though the side is not vertical, it's at an angle. Now the integral looks a little bit messy, but everything here is just a constant times L. We could take all these constants out front, and really we're just integrating L. So if we evaluate this integral, it's equal to 5,549 approximately. So that is in newtons. That's how much force is applied by the oil to one of these rectangular sides. Let's take a look at the final problem for this section. The Hoover Dam is shaped approximately like a trapezoid that is 400 meters wide at the top, 200 meters wide at the bottom and 220 meters tall. We're going to assume that the Hoover Dam is roughly vertical, so we won't have to deal with any slant height like we did with the last problem. But we want to find the total hydrostatic force exerted on the Hoover Dam. So as always, we begin by drawing a picture. Here's a trapezoid, 400 meters wide at the top, half that at the bottom, 200 meters, and then the height is 220 meters. We want to know the total fluid force of the water for the entire surface of the dam. Now, the water pressure near the top is small, and as we go deeper, we get more and more pressure. So there is more force exerted on the bottom portion of the dam and less force exerted near the top. So how do we find the total amount of force? Well, we're going to find a representative slice of the dam here and find the total force exerted on this slice, and then integrate to find the total amount of force for the entire dam. So let's first start with an expression for the force on a slice of the dam. Well, let's give this some variable names here. Let's say that this is a distance of y from the surface, and we'll say that the length here, we'll just use L. So the force on a slice, we have dF as the small bit of force. It is pressure times area. Pressure, once again, is density times 9.81 times the depth, which here is y. And then the area is L times the thickness of this slice, which is a small change in y. The thickness is dy. So the area is L times dy. This expression gives us the total amount of force on a representative slice. Now that we have this, we need to get everything in terms of y. And you might be thinking that we'll probably use similar triangles here, and that is indeed the case. However, we don't quite have a triangle, we have a trapezoid. So there's a number of different ways to work through this, but I think one of the easiest ways is to think of creating a couple triangles here. Let's imagine creating a triangle here and also here. Now, we're told that the width at the bottom is 200, so we have 200 meters between these two vertical lines. And then let's just call this length, we'll call it W for a width, and we have the same width W on the other side. So we can write L, the total length, as 200 plus 2 of these lengths W. And now that we've got these triangles here, we can use similar triangles to find the value of W. So focus on this portion of the figure here. We have an overall triangle, this one right here. And since the total width at the top is 400 meters, we're cutting off 200, so we're cutting off 100 meters at each end. Each end here we have 100, so the top of this triangle measures 100 meters across, and the height is 220. That is the same shape as this smaller triangle here. This triangle measures W across, and the height is 220 minus the height y from the surface of the water. So this height here is y. So the height of this small red triangle is 220 minus y. So we can write an expression that relates this length W with this height. That ratio equals the ratio for the larger overall triangle. So we can write here W divided by 220 minus y equals 100 divided by 220. If we solve this for W, we have W equals 100 divided by 220 times 220 minus y. This is an expression for W in terms of y. Now the total length L that we're interested in, this entire length here, is 200 plus 2W. We have an expression for W in terms of y, so we'll write that for this expression for W. So we have 200 plus. Multiplying the 2 here by the 100, we'll just write this as 200 over 220 times 220 minus y. So we have now written the length L in terms of our variable y. Let's write that in the representative force on a slice, and then we'll integrate to find the total amount of work. The density of water is 1,000 kilograms per cubic meter times 9.81 times y times the value for L, which is 200 plus 200 divided by 220 times 220 minus y, dy at the end. This expression is the total force on a representative slice of the dam. So the total amount of force for the entire dam is the integral of all these representative slices. So we integrate 1,000 times 9.81 times y times 200 plus 200 over 220 times 220 minus y, integrating with respect to y. Now this looks rather messy. There's a lot of numbers going on here, but notice that most of this is just constants. We really have a y times 220 minus y. It's actually quite a simple integral if we were to do it by hand. We just need to expand it out and then deal with all these messy constants. What are the limits of integration? Well, we integrate with respect to y, and y starts at a height of 0 and goes all the way to the entire depth of the dam, which is 220 meters. So the limits of integration are from 0 to 220. If we evaluate this integral, we get a total force of approximately 63.3 billion newtons. That's how much force is exerted by the water on the Hoover Dam.